So I will, as the title says, talk about multiscale approaches to dispersion modeling. If I have time, I might throw in some other stuff at the end, which has been, I decided to add just sort of inspired by some of the talks I've seen here today, this week rather. So I like to start most of my talks with a slide which looks something like this. And I think sometimes those of us in method development or the likes can perhaps lose touch in some ways of, what the ultimate goal of our research is. And I certainly can. So, maybe it's just me, but I don't think so. And, really what we want to do is better understand the world and also be able to predict the world. If we can predict things, then we can use models to screen things. We can use models to eliminate unnecessary experiments. We can use models to target experiments where they should be targeted. So I think it's not always a goal. Often we are interested in understanding, but I think it's a worthy goal, this idea of being able to predict things. Now I am used to speaking to chemists. So 1 kilojoule per mole is their magic number for high accuracy, sometimes 1 kilocal per mole, depending on which particular chemist you talk to. But I would argue that the most important thing really, rather than some sort of number, like good numbers are good, but we need to make sure we're able to capture the right physics in models. And I think Alex and various other members of his group have made this point really clear, which has made my life a little bit easier, that dispersion forces are one area where if you miss that physics and if you miss the real physics behind dispersion forces, then you can really go wrong in quite a few systems. So on that note, I'm going to start with a little bit of a personal history. So I've worked in topics related to dispersion forces for a long time now, which means I've been around long enough to have seen a wide spectrum of commentary on the topic. So I can remember, in 2007, basically, people, and these are all paraphrase quotes from the actual year. So people saying things like, basically, oh, you don't need dispersion forces. We've got PBE or B3-LIP or whatever. By 2012, we'd seen this massive transformation, really, in what people expected. Suddenly, you had to include dispersion forces, no matter how crap they were and how unnecessary they were for the problem. If you didn't have them, you might get criticized. So by 2017, we see, comments along the lines of, well, we've got the D3 correction, which is an excellent correction. I'm not going to knock it, but therefore this is enough. Well, I think we've seen enough talk so far, which suggests that isn't enough. And I'm going to highlight one realm where, even things like MBD and stuff can break down, and that's in the sort of material space. So this on the right now, this is a completely non-dispersion bound system. This is solid potassium, but we can see some really drastic failures of D3 here, for example. So if you use your dispersion correction, you get an incorrect double minimum. Now, we know why this happens, but this is just to illustrate that, solved problems aren't always all that solved. So I think even in 2022, there's still room for improvement and there's room for deeper understanding. And there are a few topics which really at a sort of fundamental theory level are still a little bit unresolved in dispersion. So a lot of the problems historically and historic understanding of dispersion forces, and again, Alex touched on this, but I'll repeat it in a slightly different way just to put my own spin on it. Is this idea that as a general rule, traditional approaches to dispersion have basically said, okay, we know that, we've got this asymptotic minus C6 on D to the 6 contribution. And if we just add this up between every pair of atoms in a system, we get the van der Waals. energy. Now, a different perspective on this, which I think was touched on in one of the previous slides, is basically, okay, if we take an atom in the top row of our 3 layers, then we get a little positive charge here and a negative charge here from a quantum fluctuation dipole. And of course, this positive and negative charge here, this dipole gives an interaction that falls off as 1 on d cubed, going down to the bottom layer, sets up a negative, positive, and this couples back with another 1 on d cubed, so you get your 1 on d6 out of it. And you just do this for every pair of atoms in the system. Now, if you add these up, you can explain the properties of different types of geometries. This has been going on forever. So, for example, if you wanted to look at the interaction between 2 parallel 1D wires, hopefully you can see my fingers pulling them apart, then that interaction per unit length actually would fall off as 1 over the distance to the 5th. If you've got 2 2D layers and pull them apart, you'll get an interaction that falls off as minus C4 on D to the 4. And if you take 2 bulks and pull them apart at the surface, you'll also get a minus C4 on D to the 4. And these are basically just geometric arguments, so nothing too exciting. But what these non-additive theories miss is the fact that we don't just have 2 atoms in our system, we have multiple atoms. And each of these atoms, of course, is setting up an electric field from its spontaneous dipoles, which is affecting another atom, which is affecting another atom, which is affecting yet another atom. So, for example, our pairwise terms, basically, we've got our field, as I described before, feeding back 1 on d6. Now, if we have 3 atoms, this is long enough known that it has its own special name. It's the Axelrod-Tellermuto term. And we basically just look at the sort of combined interaction between the 3. So, for example, our positive charge here and negative charge here is definitely going to set up a negative here and a positive here. Now, down the bottom one, probably this is going to be a positive, but it's going to be a little bit of a weaker positive because the one up here is positive. So what will actually kind of happen is everything will stabilize into a sort of 3-way coupled fluctuation. Now, when it gets really interesting is when you consider that we have atoms sitting next to each other. So these are layers. So we've got a periodic lattice across here. It could be wires either. Doesn't make any difference to the concept. So we set up a little dipole here. Well, there's a negative charge here. That's definitely going to set up a dipole right next door. And it's going to be quite a strong coupling between these two since they're right next to each other. So we can put in the field lines if we want. But the point is, this now looks, so once you're at the next atom, you're kind of far enough away that you're no longer seeing this as 2 atoms. You're just seeing this as an extra long dipole. So in our second layer, okay, well, this will interact with 1. But similarly, and I'm going to take my pen out here. So for example, we have a coupling over 2 there. So that will couple to 2. That will couple to 2. And of course, we keep getting coupling. So what we can actually do is get coupling between layers or wires at longer scales, which sort of look like extended, they're not just a single atomic thing. They are a collective sort of polarizability mode within the layers. And it turns out that if you've got a metal, then these collective modes are so strongly coupled, and this is not surprising because a metal has, 0 band gap, it has good conductivity. Basically, electrons can move a long way at fairly low cost. So this sort of mass coupling happens so strongly that it fundamentally changes the actual asymptotic interaction law. So rather than having a minus C4 on d to the 4, we end up with a minus C5 halves on d to the 5 halves. This is 1.5 powers different. So this is a case where not only is beyond additivity numerically important, quantitatively important, it's qualitatively important. It changes the fundamental nature of the long-range interaction. So how do we explain this? How do, that's an example. You can work it through, and I'll show some others in a second. But, why can this sort of thing happen? And I look at this in what I call the sort of platypus theory of dispersion. And the core concept here is that the whole is weirder than the sum of the parts. So if we took second order and added third order and added fourth order, we would not get to this relationship. It's only when we take everything together that we get something weird. So why the platypus theory? Well, this very cute little fellow here is a platypus, and they are native to Australia. They only appear in Australia. They are extremely hard to keep alive in captivity. But let's just look at what goes into a platypus. It's a mammal. It's got fur. So that's pretty typical. Nothing unusual there. It's got a beak like a duck. Well, that's a bit stranger. But, if you compare it to something like a tapir or, other more unusual mammals, it's not especially strange. Now we get to something extra strange. It lays eggs. That's strange, but there is a second mammal which lays eggs, an echidna. So we've got two. All right, we're still getting pretty weird. It's also got poisonous spurs, and as far as I know, it is unique amongst mammals for its ability. This is probably venomous. I can never remember the difference, but it's unique, as far as I know, amongst mammals for the ability to produce poison or venom. So a platypus is just plain strange, but it's not strange because of any two effects in there. It's not even necessarily strange because of three. I mean, a mammal with fur and eggs, weird, but there used to be heaps of them before they got driven extinct by placental mammals. Eggs and poisonous spurs, okay, that's not surprising. There's plenty of reptiles with this, beak of duck and eggs, duck. So we can see here that it's only by taking every bit of the platypus that it really gets strange. And so strange that when the first descriptions and samples were sent back to Britain from Australia very in the early days of the colony, basically they got a stern letter back saying, don't play April Fool's jokes on it, which is relevant to you, but not me, sorry. So platypi, weird, dispersion forces, weird. So we want to explain this. What goes into making a system have dispersion forces that are greater than the sum of parts, and what goes into a system just having something that can be represented pretty accurately by a sum over C6 coefficients? We know a sum over C6 coefficients works well a lot of the time. But we also know it really doesn't work very well some of the time. So I've worked a long time with Professor John Dobson, and after many years of him being perplexed and sort of trying to marry sort of chemical concepts with more solid state concepts like Lifshitz theory and Casimir theories, he sort of broke down this idea of non-additivity and these weird effects into three types. So the first of these is literally everyone does this. This is a long solved, long known problem, and that is basically a carbon in vacuum, a carbon atom in vacuum does not have the same polarizability as a carbon in methane. Don't think anyone's going to be too surprised by that. Type B effects, and I have to admit I paraphrase these a bit, so if you want John's original definitions, you should look in his paper, but type B is many body effects which come from electrostatic coupling or screening. So these are the effects that are in many body dispersion model, for example. And I like to look at these in some sense as a sensitivity to a global geometry, and I'll talk about that on the next slide or one of the next slides. And finally, there's band structure effects. And these are basically what happens if you have a small gap or a zero gap. And that's where you really get the sort of, platypus dispersion forces, the really strange ones. And these are highly collective. So how do we actually make a platypus if we want to engineer a system to have unusual forces? Well, the sort of key ingredients are basically threefold. You need one long dimension in your system. You need one short dimension in your system, and you need a small or zero gap. And this, of course, would be an extremely uninteresting problem were it not for the fact that in recent years there's been a fair bit of interest in things like 2D materials. And although it's dropped off, there's still a fair bit of interest in things which are essentially 1D materials, like nanotube. So these systems are really important in a dispersion sense because, well, A, most of the binding between things is dispersive. They kind of fizzy-sorb to each other. They have these qualities, long dimension and a nanoscale dimension. And in some cases, especially some of the ones that people are interested in, they have a smaller or zero gap. So suddenly these sort of, what would be essentially a mathematical quirk starts becoming something which is a bit more relevant. Now, a lot of the platypus can be got from the level of many-body dispersion, and this has been talked about a lot, an excellent theory. One thing I wanted to highlight was actually an application of this from 2012, because it just makes such a clear illustration of what goes on. What do we have here? So this is basically an example where many-body dispersion becomes important. What do we have? A long and thin system. Here we have a long and thin system. So you can see that, there is a sort of blurry line between B and C, and I'll actually talk about some of the issues with that in a little bit. So this I wouldn't quite call a platypus, but, it's still a weird creature. Now, if we want to do these things sort of, properly and capture the full collective behavior, it's extremely hard. And in fact, you can't really do it at the atomic level. And the reason for this is pretty simple. It's that these are collective effects. So the way we actually can get these insights, the way we could derive the minus C5 halves and D5 halves before, and the way we can show that layers of graphite interact with a minus C3 on D cubed, again, not what you would expect from an additive theory, is essentially by going back to the random phase approximation. So this is there's variants of random phase approximation. I mean, the simplest one, basically. So we can go back to the random phase approximation, but rather than solving it in full, what we can do is we can recognize, and of course, this has already been raised in I think, a couple of talks so far in this meeting, that tight binding physics, in a sense, can become sort of relatively exact in certain limits. And there are pretty strong arguments that a tight binding model of the response of, say, graphite or a metal also becomes relatively exact for dispersion interaction. So basically, we take a tight binding density-density response model at low wave number for graphite. We shove it through some multiple integrals, and we arrive at a minus C3 on D cubed instead of a minus C4 on D4. So Dobson, White, and Rubio first published that in 2006. And a few years later, we managed to sort of, show this using quite expensive random phase approximation calculations, which I won't talk about these ones, but I'll talk more about those sorts of calculations in a bit. And again, I remind you, long, thin. So let's take an example. So we'll just stick with graphene for a second and think about what happens as, in a sense, we remove thinness from our problem. So this has become better known, but there was a long time actually where even experimental literature was very ambiguous about what people were actually measuring when they were trying to measure things like binding energies between graphite or whatever. But there's basically three ways you can define a binding energy between graphite, a binding energy within graphite. So I'm not talking two graphenes. there's only one way that I can think of to define that. But if we have bulk graphite, there's sort of three ways you can describe energetics. So we've got a stack, if you imagine it like a stack of playing cards, basically. So one way we can define it is we pull all our playing cards apart equally. So we just take our playing cards, spread them out, and this is basically the same as a pair of layer problem. In fact, it's very close to what you'd get out of a pair of layer problem. Now, a second way we can define it is we've got our stack of cards, we peel off the top card. Now, this is not quite the same as stretching everything out. And there's a third way, which we don't peel off the top on, we split our deck of cards in the middle. And what's really exciting here is that if you think about it, when we pull all our layers apart together, so they're all spaced at distance d, we preserve nanoscaleness. So each layer is still nanoscale thick, and we get, as predicted, this minus C3 on d cubed. And what I'm showing here is the ratio of this to the additive reaction. So we divide minus C3 on d cubed by minus C4 on d to the 4, and we get a scaling of d. If we exfoliate, so this is taking one just from the top, then one of our layers is nanothin, the other one is on the top of a bulk. And what actually happens is you reduce this change to the scaling by a logarithmic factor. So it still behaves kind of like layers, still getting the d, but it's reduced. Now, if you split your two things in the middle, you get, at least in scale terms, exactly the same result as you do for an additive theory. So we can really see here and pin down, okay, this is, this nanoscale business is really important. And I probably won't talk about this, but no, I'm not going to talk about that later. So that's type C, and type C is interesting. Probably in reality, I can't think of many problems where it's going to be vitally important. But it's certainly likely to be somewhat important in certain cases. And the problem is that the cases where this sort of type C non-additivity is important are also cases where type B non-additivity are important. So type B non-additivity is also enhanced in these things. And this actually gives a slight issue here, and I've stolen this slide. This is kind of like a more pedagogical version of these two bits here. Sorry. So we've got this Dobson B, which is really incredibly well modeled by many-body dispersion. Okay, you can improve things in materials a little, but on the whole, it's excellent. We've got this Dobson C, which can be explained very well by doing low wave number type binding or nearly free electron type calculations. What's really hard is actually joining these two things together. So bridging these two limits becomes very hard. And I thought I'd throw this question out here today, just because we do have a bunch of mathematicians who specifically work in multiscale modeling. And I think if there's ever an audience that might know the solution to this sort of problem, it's this audience. So when we look at type B, we have a bunch of point dipoles, basically, or smeared point dipoles, however you want to define them, which are localized in real space. When we have type C, we have a response function which is localized in reciprocal space. So the question is, how can we come up with a seamless connection between these two locality regimes? So we need a sort of, methodology and a way of understanding how to seamlessly transition from local in space to local in reciprocal space without losing the sort of important physics that's there. And I mean, one thing I've sort of often thought about, and there's been some nice work on this recently, is stochastic approaches. But the more I think about it, the less I think stochastic approaches are actually going to help us here. my suspicion is that there's possibly some nice mathematical tricks or something that can help to bridge this gap. And this is an important gap to bridge, because if you want to start looking, for example, at microscale devices or nanoscale devices, you need to be able to take into account these two physical regimes in a realistic way. So there is one method which does include everything. It doesn't include everything. It includes types A, B, and C, and that's the random phase approximation. And this is I've used the random phase approximation before. That was an approximation to the random phase approximation based on type binding. Here, I mean the true random phase approximation, in the sense that you actually take into account the proper electronic structure of your system. And this sort of, full random phase approximation, I'd call a sort of bronze standard benchmarking approach. If you've got a system which is heavily dominated by dispersion forces, it's probably pretty good. Certainly it captures types A, B, and C non-additivity. It is seamless. There's no sort of, issues with scales or double counting or anything like this. On the other hand, it's really expensive for the sort of, realistic systems you might like to look at. And it also has some problems with short range physics. So I show you some nice, sort of results we got out of the random phase approximation. So there's two fun things in this work. So basically what we did is, there's been this long-standing puzzle in the community which experiment's been unable to resolve, which is whether or not the graphite or diamond structures of boron nitride. So boron nitride is, pretty much a straight analog of carbon. So it has a diamond structure, it has a layered structure. And, for carbon, this is well known, and I've actually forgotten the answer, which one is lower. But, whether or not at 0K, the diamond structure or the layered structure were more stable. So we thought, okay, great. This is exactly the sort of problem where the random phase approximation is likely to work well. So it served two purposes. One, we could actually make a prediction about what was going on in boron nitride. Experiments had not been able to resolve this. And two, we could actually test the ability of dispersion corrections to reproduce this prediction. So we did a lot of nice work. Not nice work. We did a lot of hard work. And eventually came to the conclusion that some dispersion corrections were not that great, others were better. And most importantly, we predicted that the random phase, the diamond structure was in fact the most stable structure for boron nitride. But hot cup of coffee, 80 degrees C, the two switched. So this was kind of fun. Got a paper out there. There was another fun bit about that. This CM2 is a potentially new polymorph of boron nitride, which was discovered by typographical error. So that was good fun too. So this was wonderful. Since then, however, and this is the danger with using something like a bronze standard approach, is that these problems with short-range physics I mentioned before, well, turns out they were quite important here. So since we did this work, there have been sort of 3 different studies from 3 different groups, all of which have predicted that we were in fact wrong. So that's a lesson to us all, is that sometimes you can throw good theory at something, doesn't always mean it's right. Well, I'm going to assume that these 3 higher level theories are probably more likely to be right than we were. So anyway, just that amused me, so I thought I'd throw it in. Nevertheless, random phase approximation is very useful, and when you do have things that are bound by dispersion forces, so I've spent this last week sort of listening to slides and throwing in some new ones where they've been relevant to what people were talking about. So, for example, in these Moire lattices in graphite and in boron nitride, these are quite sensitive. Well, they are sensitive to the distance between things, and as you rotate, then you get more, like your atoms overlap more, so the layers actually will pull apart a little bit and come in. So that was talked about quite a lot. So we this is exactly the sort of problem where you expect the random phase approximation to do a good job. We tested this, we came up with parameterizations, and we also discovered that the local density approximation does almost identical. So yeah, I guess this is like greatest flops slide or something. Anyway, so that's good though, actually. I mean, because these random phase approximations are quite expensive and local density approximation is not quite expensive. So it means you can actually sort of, do a lot of stuff about the Moiré cells and potentially actually do real calculations to test cheaper models and stuff. And last but not least, so this is sort of getting more into the issues that you get in multiscale problems. So if you take a zeolite and put, say, methane inside it, then the methane will very, very, very weakly physisorb to the zeolite. So this is an extremely weak interaction, and it's extremely temperature dependent. So if you do this at room temperature, we basically get an adsorption enthalpy, I guess it is, of -4 kilocalorie per mole. So this is quite tiny. And what's important here is basically we have an extreme sensitivity to dispersion interactions and simultaneous with thermal issues. So we basically, this just describes a sort of approach and where we did some resampling of the thermal statistics, or in a sense to capture the dispersion forces more accurately without using millions and millions of CPU hours. And so I like, these are sort of almost benchmarky type problems on which you can start to dig down of whether or not lower cost approaches work well. And of course, as I've said, we can't do random phase approximation on large systems. What random phase approximation can hopefully mostly do, except where it couldn't before, is give you insights into whether or not you're actually right with your lower cost. So we do want to capture dispersion usefully, and of course, the many-body dispersion model does a fantastic job of it. So does Grimmer D3 actually in the right situations. So we have these models which do an absolutely fantastic job of things. There is a bit of a problem though with these models which do a fantastic job of things, and this is an important problem when it comes to understanding real systems, and that is that for the most part these methods are designed and heavily tested on main group elements. Now there are maybe 10, 15 things which you might consider main group in the sense of things that are in major benchmarking sets and biological processes or whatever. So a lot of chemical research and chemical physics research focuses on these sort of 10 to 15 elements. In your iPhone you have 75 elements, and there are 80 elements stable in the periodic table. So the iPhone's using almost all of them. So where is this huge difference? This huge difference comes from the fact that an iPhone is chock full of designer materials. These are inorganic chemistry. These have multiple metal atoms interacting with multiple other things. Different parts of the system have different elements in them. So if you want to have an ability to predict a new battery technology, for example, if you want to say, okay, we reckon that this class of materials might be good for batteries, let's try varying a few molecules in there. We need a method that can take into account the sort of very much more diverse chemistry that you get in materials problems. And some of these that are sort of problematic, so you have ionic effects in there often, you have ionic crystals, but you have sort of partial ionicity and all sorts of things in there. These are often strongly polarizable materials, and in some cases, the reason these materials are interesting is because they're strongly polarizable. And of course, we do worry about metals, and sometimes these are real metals, gold nanoparticles. That's pretty metallic. So we need an approach that can actually do these. So we sort of been working on this for a while, and Oh, I've forgotten to put the thing in there. I can't even remember what year it was. Sorry. During COVID, this is my broad term for that period, published this work, which basically combines many-body dispersion model with a fractional ionic charge model of polarizabilities and throws in some smeared dipoles. And what we were able to do was basically to cover a sort of very diverse range of physics and chemistry, or chemical bonding, I guess. So not necessarily going to be by being the best at anything, but by not doing a bad job on anything. So, and this includes metal. So remember right back at the start, we had that slide which showed things not doing very well for metals. Well, problem avoided. So basically the two sort of additional ingredients on top of Alex's work here is the use of a smeared dipole, which is basically to avoid issues in metals, and taking into account the polarization physics of fractional ions in them. And you can sort of, get rid of a lot of the problems that happen in solid. And that lets us, for example, address this particular problem, which is a fairly typical materials type problem, where we're interested in lithium intercalation. So what we need to understand is bulk lithium, metallic, bulk cobalt dioxide, a layered material, lithium intercalated. I've been doing too much of the latter lately. Lithium intercalated in the cobalt dioxide. So this has got two effects here. So one, we've got the interactions between the lithiums and the layers, but two, of course, the charge from the lithiums disappears. So we've essentially got lithium plus with a bunch of CO who knows and O who knows. So we're able to take into account that fact that, maybe the cobalt does not have a full charge, it's got half a charge. 2020, there you go. It was just a COVID. So end result actually works pretty well. So, okay, I'm not going to talk about this because Alex actually talked about it on Monday. And I thought I'd finish off my sort of, discussion on dispersion forces with what I consider to be the sort of last big open problem in dispersion force modeling. So this matters at whatever scale you're interested in. So as far as I am concerned, or as far as I'm aware, maybe there's some wonderful paper out there which explains it, but I have never seen it. Is that there's actually not a no comprehensive or sort of mathematically robust way of understanding dispersion of excited state. So there's a few problems in this. So there's some actually quite complicated definitional issues. How do we actually define what a dispersion force is? Fluctuation theorems change when you start from an excited state, and I'll actually talk a little bit about that in a second. We need a sort of mathematically and physically rigorous way of understanding these problems. You have to be extremely cautious once you have excited states about doing things right. And there's another thing here, which is basically that, excitations have finite lifespans or can be driven or whatever. So you might have cycling between low and high energies or whatever. So the question is, how do these time scales affect these quantum fluctuations? So the bit I didn't really mention, in fact, I think every talk on this topic has brushed it over so far, but these spontaneous polarizabilities on atoms okay. So Heisenberg uncertainty principle was mentioned, and certainly that's true. But in reality, what's actually kind of going on is an attempt to pull in virtual orbitals in order to lower an energy in the presence of the neighbor. So that's a different perspective on it. And this does have a timescale associated with it. So each of these excitations has a timescale associated with it. And there is a big question, like if we're mixing into an excited state, how do decay rates affect things, et cetera, et cetera, et cetera. So for example, if we wanted to, look at multi-scale modeling, sorry, I'm trying to drive my Zoom window away. For example, if we put, I'm guessing, I don't know, I just stole this picture because it looked nice, like a gold nanoparticle on a surface, how is this going to affect, dispersion interactions nearby? And this could be quite important. This is exactly the sort of problem where dispersion forces really are, and can be quite important. So I hope there's an answer to that someday. And if you're really, really, really interested in all this stuff, a lot of it's in a book. Right. So at the start of the talk, I added an "and other stuff." And this was basically, I decided to throw it in because, because I'm last and I could. So I've been here for a week. I've been, getting up at 2 a.m. locally and watching all these, really nice talks and getting really excited and learning a lot about things like embedding theory. And so the concept of, the importance of idempotency or of not bothering with idempotency have been mentioned, I think, in at least 2 talks, possibly 3. So I just wanted to sort of throw in a bit of stuff about, what I've been having a lot of fun with lately, which is ensemble density functional theory. And ensemble density functional theory, in some sense, can be thought of as a way of applying a DFT type approach of rigor to open systems. So I just you can ignore this picture. I just got jealous because everyone has nice pictures and I have too many words. So ensemble density functional theory is basically, well, as the name suggests, density functional theory for quantum state ensembles, not classical ensembles, but, well, I suppose it could be. And so the idea here is basically that you have theorems and behaviors which connect, or so you're allowed to connect your quantum system of relevance to a bath. And that lets you, for example, choose a non-integer number of electrons in your system. And this is actually what I did in the fractal ionic model I talked about before. You can have systems which are open to energy in the sense that we can, for example, have a mixture of a ground state and a single excitation and study that simultaneously as a whole. And of course, if you take derivatives with respect to your weight here, you can get like, excitation properties. And of course, you can have something that's open to both, whether this be an arbitrary mixture of excited state. I mean, I don't know why you would, but well, actually, I do know why you would. There are some really good work by Emmanuel Fromage on choosing these to sort of resolve important problems. But the obvious other examples are things like thermodynamic ensembles. So if we've got the grand canonical ensemble, then we have openness to particle exchange and openness to energy exchange with the bath. And dealing with any of these systems is absolutely guaranteed to get you not guaranteed in every case, but as a general rule, is guaranteed to give you a non-idempotent 1 IDM. So we've been having a lot of fun in recent years, essentially redefining the textbook in the context of ensembles. So essentially, once you start putting in these ensemble considerations, certain things which quite literally do appear in textbooks, certain equations just aren't valid anymore and don't follow. So I mean, the sort of key one is that, when people talk about density functional theory, they say, okay, the Kohn-Sham state is a single slater determinant. Well, it's not always. So we managed to show that in 2017 by using ensemble arguments. So you have configuration effects in there. We're able to sort of use the fluctuation dissipation theorem to redefine exchange in a way that was consistent with exchange in a typical scenario. So all of these agree with what you'd normally expect, but what they do is they use they use fundamental relationships of quantum systems to explore the breakdown, or the partitioning, in a sense, of different types of energy terms. So, for example, to do Hartree exchange, you need to base it on a rigorous, mathematically rigorous functional, which is the universal functional. So how do we get the Hartree exchange out of that? We take its derivative as lambda goes to positive 0. So this is well defined. It's a well-defined functional. Well, yeah, up to axioms in the ingredients, but so you can get this out. Exchange, how do we define exchange? Well, we define exchange as the non-mean field part from a fluctuation dissipation theorem. So how do we define Hartree? Well, that's the mean field part of fluctuation dissipation theorem. So in a sense, what we're doing is we're replacing the usual chemical type intuitions in these things by mathematically well-defined objects. So this gives us some nice results. So for example, we actually had to, I'm sure this has been published somewhere before, but I actually have never seen it and we couldn't find any examples of it, which is basically a quantum fluctuation dissipation theorem for passive states. The passive states are basically, okay, I won't talk about what passive states are. And this is really interesting because you might have noticed on the previous slide, we have these max in here. And here we have a min. So these are actually, you can exchange the min and the max outside and inside for a passive state. So these are sort of equivalent ways of writing the same thing for passive states. And the point here, how am I doing with time? Sorry. So we end up with these, very unusual terms appearing in fundamental relationships that ordinary, you just assume are well behaved. And so this problem right here is actually related to one of the difficulties of defining dispersion between excited states, actually. And get some nice results out. So for example, on the topic of things obeying or not obeying the Aufbau principle, well, as soon as you have a non-idempotent 1 RDM, even the question about what the Aufbau principle actually means starts to become a curiosity. So I don't think breaking Aufbau there has any problems at all. It's a jolly good idea. And that's it. So I want to thank you all for sticking around till 5 on a Friday. I hope you have somewhere fun to go afterwards. I'd like to thank many good collaborators and my group members, funders, and I'd really like to thank the organizers and IPAM. This has been a really exciting conference, even though I'm not actually there in person. I've enjoyed all the talks. It's been a really great experience. And look, I think we're done. So conclusions, basically, we do need to worry about materials. Okay, so that's my conclusion. Just cross that out. Worry about materials. This is essentially what I do at the end of lectures when it's late on a Friday. Thank you all.